answer the questions that you didn't get to as we're moving forward here. So feel free to fill them in. Okay, so this enzyme pyruvate carboxylase proceeds really through almost three active sites. Okay, there are three effective reactions that are happening here. Okay, the first one is activating carbon dioxide to be reactive, right? Because carbon dioxide in itself is really not very reactive. When we put it in water, I mentioned that it becomes bicarbonate, which is shown here. But bicarbonate is still not very reactive, right? Bicarbonate has 3 resonance forms. It's just stable. It's fully oxidized. It's just stable, right? So we have to activate it to be more reactive. And that's where this biotin carboxylase domain comes in. The first thing it catalyzes is the activation of carbon dioxide. And it does so by putting a phosphate onto the bicarbonate. And we end up with this molecule carboxyphosphate. And I'm highlighting carboxyphosphate here, number one, because it is the activated form of CO2. It is the reactive form of CO2. Also, we're going to see it a lot more this semester. Whenever we are dealing with CO2 moving around, we're talking about biotin and we're talking about carboxyphosphate. These are the activated forms of CO2. Carboxyphosphate is important because it is how we hang on to the energy of ATP hydrolysis, right? It's how we transfer the energy of ATP hydrolysis into something useful. The bond between the phosphate and the CO2 is not stable. It's a reactive bond. So breaking that bond produces energy. So making that bond stores energy. And that's the value of this molecule, carboxyphosphate, is storing that energy. Okay? In the second step, once we make our carboxyphosphate, we then transfer the CO2 functional group onto biotin. Okay? Biotin is actually, and we'll see this in a second, is covalently linked to this carrier protein called the biotin carboxyl carrier protein. And the really cool thing about this, and this is the first time we're going to see it this semester, and we'll see it again and again, is that this domain is almost like Tarzan, right? Swinging from one tree to another. So we have our biotin carboxylase domain, which is at one spatial site on the enzyme. And then the rest of it, the pyruvate carboxylase domain, is another part of the enzyme. And it's this biotin carrier protein, this BCCP, that moves the CO2 from one site to the other. Okay? So in the next step, we start with biotin covalently bound to the enzyme. It reacts with our carboxyphosphate, our activated CO2. The CO2 gets transferred onto biotin. So we now have the covalent bond between biotin and CO2. We release inorganic phosphate. So now the energy of ATP hydrolysis is trapped in the bond between biotin and carbon dioxide. Okay? The biotin carboxyl carrier protein then swings over to our other active site. Now that it has CO2 on it, it swings over to the other active site where the CO2 is transferred from biotin onto pyruvate. And at this point, that reaction is driven by breaking the bond between CO2 and biotin. And I'll give you all a second to kind of jot stuff down. But remember, I'll have this posted online so you can see it. Okay? The one other thing I want to point out here before we look at the structure of this enzyme is that this is an interesting aspect of this, is acetyl-CoA, which we haven't talked about a lot yet. We've mentioned it, but not a lot. Acetyl-CoA is an allosteric activator of biotin carboxylation. Okay, this is interesting because acetyl-CoA is a really, really important intermediate in the cell. It's the product of fatty acid breakdown. It's the starting point for fatty acid synthesis. And it's the entry point into the TCA cycle. So the idea here is if we build up acetyl-CoA, that means that we have a buildup of cellular metabolites, right? We have a buildup of the central metabolite. So a buildup of this activating biotin carboxylation triggers gluconeogenesis. So it all kind of makes sense. It's a way of saying, all right, a buildup of acetyl-CoA means we have a crap load of cellular energy. Let's activate enzymes that can help us store that, right? So we start moving molecules back through gluconeogenesis so we can store some of that energy in the form of starch or glycogen. Okay, so here's pyruvate carboxylase. I mentioned that there are two important enzymatic domains. The BC domain is our biotin carboxylation domain. This is where we activate CO2 to become carboxyphosphate, and it's where we put the CO2 onto biotin. Okay, biotin is covalently linked to this BCCP, the biotin carboxyl carrier protein. The PC domain over here is our pyruvate carboxylase domain. This is where we put the CO2, we take the CO2 from biotin and put it onto pyruvate. And they're linked by this tetramerization domain. So the idea here, as the name suggests, is the quaternary structure of this enzyme is a tetramer. So we have 4 of these functional units all together, meaning that we can have 4 of these reactions happening at the same time, making the overall process a lot more efficient. Okay, so we start off in our BC domain where we have CO2, bicarbonate, and ATP bind. We catalyze the synthesis of our activated CO2, carboxyphosphate, and then the biotin comes into the BC domain. We transfer the CO2 onto our biotin. That then triggers the movement of the biotin carboxy carrier protein domain over to our pyruvate carboxylase domain. At that point, the CO2 is moved from biotin onto pyruvate, giving us our product. Okay? Any questions? All right. Now the second enzyme, PepCK. So this is phosphoenol pyruvate carboxy kinase. So the name is actually named for the reverse reaction. Starting with PEP, adding CO2 to it, and kinase, right? So we involve ATP or GTP hydrolysis or phosphate transfer, okay? But overall, the idea is that we are starting off with oxaloacetate and we are ending up with phosphoenol pyruvate, okay? And there are 3 steps and 2 of them are very much linked, okay? And in your activity, and actually, why don't y'all just kind of like work through this part of activity as I talk through it, just so that we make sure we get through the stuff we need to today. So 3 steps. The first 2 are very, very much linked, okay? So in the first step, we have decarboxylation of oxaloacetate, okay? And this proceeds in a way that you'd expect, right? Remember, I tried to stress a lot that decarboxylation always happens in the same way, okay? So here we have the electrons from on the negative atom of our CO2 group becoming a pi bond between the oxygen and the carbon, and then that then triggers the electrons between C3 and C4 to move up. And here we end up with this intermediate where we have the keto form of things. Okay, so we decarboxylate oxaloacetate and we end up with a keto intermediate that has a carbanion on C3. And the reason I say that this is very much linked to step 2 is because step 2 is the keto-enol tautomerization. So we are going to be able to transfer this negative charge onto the oxygen so that we can stabilize that charge. Okay, so we are going to move the negative charge over to this oxygen to make an enolate. And I noticed when I was looking over this that I have an error right here. That should be CH2 neutral, not CH positive or negative. Can't tell what it is. It's a negative. It's right on your sheet? Okay, good. Good. All right, so so the idea here, right, is that we are just tautomerizing this so that we can put this negative charge somewhere stable. Okay, that's important, right? Especially when we look at the active site, we're going to see that in the active site, there is a cation positioned right here, right? So there's a cation positioned right there to stabilize that oxyanion that forms, okay? There are very few instances where we can create a stable carbanion. The cofactor TPP is basically the only one. So instead of having this carbanion form and expect it to be stable, we move that electron density over to the oxygen and form an enolate intermediate that's stabilized because of the positioning of a positive charge to favorably interact with that negative charge. Okay? At that point, we can now, or at this point, we can now revert, right? So the electrons here can flow back, reform our pi bond, and the electrons in the pi bond between C2 and C3 can reach out and pick up a phosphate from GDP, giving us our product. Okay, so I'll talk through this one more time. Step 1, decarboxylation, always happens the same way. Step 1 shows the production of a carbanion, right? We produce the carbanion on our third carbon, on carbon 3. We know that carbanions are not especially stable, okay? So step 2, this carbanion gets stabilized by shifting to the enol tautomer. And that enol tautomer is stabilized because of the positioning of a positive charge of a cation in the active site. But we know that ultimately we want to put a phosphate. Hang on, I just screwed that up, didn't I? Sorry, y'all. I'm trying to put the phosphate in the wrong place. So this oxygen, Kenny, is that why you look at me weird? Okay, you should have said something. It's a sorry. If I do stupid shit, y'all should tell me. And then right, and then we put it there. For real, y'all. If I do something stupid, y'all should tell me. I assume that Kenny's not the one who catch my mistakes, so I. All right. Okay, so we put so the phosphate goes onto carbon 2. Okay. Make more sense? All right. I'm glad I went back over it because I caught my stupid mistake. Okay, so this mechanism is reasonably straightforward, and I mentioned that the enol tautomer is stabilized by the positioning of a cation in the active site. So here, if we look at our structural analog, we see that right here, right, so this is oxaloacetate, okay? So no reaction has happened so far. We see that here's CO2 on C4. This is the one that gets decarboxylated. This is C3. C2, we have the OH, and positioned next to that is a magnesium, okay? So once this gets decarboxylated, we move the electrons, we break this bond, we form a double bond here, and that negative charge gets stabilized based on the positioning of that magnesium. And this spot right here is where the gamma phosphate of GTP would be. Okay, so the enzyme is structured in a way that it can very much stabilize that high energy transition state. And that brings us to the end of gluconeogenesis. And that's it, right? So we know that all of the reactions in glycolysis are directly reversible. What? Okay. So all the reactions in glycolysis are directly reversible except 3. Step 1 is hexokinase or glucokinase, right? Phosphorylating glucose. That can be directly reversed by decoupling ATP. Okay, so we simply hydrolyze glucose 6-phosphate to give us glucose. That's spontaneous, catalyzed by the enzyme glucose 6-phosphatase, G6Pase. The second irreversible step was the phosphofructokinase step, putting the second phosphate onto fructose 6-phosphate to give us fructose 1,6-bisphosphate. Just like step 1, we reverse that by decoupling ATP hydrolysis and simply hydrolyzing the phosphate off of carbon 1 of fructose 1,6-bisphosphate. This is catalyzed by FBPase. The last irreversible step, pyruvate kinase, is not directly reversible. Okay, so we have to go through a couple extra steps. Step number 1 is we take pyruvate and we transition it, we move it into the mitochondria where we find the enzyme pyruvate carboxylase. We consume ATP, we consume an equivalent of CO2, we make oxaloacetate. The oxaloacetate then diffuses back into the cytoplasm where we find the enzyme PEPCK, we consume GTP, we produce CO2, and we end up with our product, phosphoenol pyruvate. Phosphoenol pyruvate is then in equilibrium with everything back to fructose 1,6-bisphosphate, where we can find FBPase to reverse that reaction. Right? Everything else is in equilibrium. Okay, so overall, the free energy change of gluconeogenesis, of converting 2 pyruvates to 1 glucose, is quite spontaneous, minus 48 kilojoules per mole. Okay, the one thing that I really want to point out is reversing glycolysis is not a zero-sum game. Okay, if we were to directly reverse glycolysis, we know that we would consume 2 equivalents of ATP, we would consume 2 equivalents of NADH. But that's not what happens. Instead, what happens is to convert 2 pyruvate to 1 glucose, we can't directly reverse it. Instead, we have to go through these extra 2 steps to convert pyruvate to phosphoenol pyruvate, which ends up consuming more ATP. So glycolysis produces 2 ATPs and produces 2 NADHs. Gluconeogenesis consumes those 2 NADH, but it consumes an additional 4 ATPs. Okay, so we directly consume 4 ATPs and directly consume 2 GTPs, but remember, GTP consumption is energetically equivalent to ATP consumption. So effectively, this is consuming 6 ATPs to make 1 glucose, right? That is 4 more ATPs than glycolysis produces. So reversing glycolysis, the gluconeogenesis pathway, is not as favorable as glycolysis, as you would hope reversing glycolysis would be. And this is a common theme, right? In metabolism, it is common for the anabolic pathway to consume more energy than the catabolic pathway produces. And a really big reason for this is that things aren't perfectly efficient, right? When pathways happen, when reactions happen, we hope that all the energy is trapped in the form of ATP or NADH, but it's not. Some of it's lost as heat, right? Which is why our bodies radiate heat. Okay, David, do you have a question?
I was just going to ask if it follows the same
So yes and no. So yes, in the energetic sense, GDP is converted to GTP, which is then converted to ATP. So effectively, yes. So there's we actually kind of talked about this at the beginning of our metabolism discussion. There's this enzyme that will readily take ATP and another nucleotide diphosphate, any nucleotide diphosphate, and it will transfer the phosphate from ATP onto the other nucleotide diphosphate, giving us a nucleotide triphosphate and ADP. Okay, so this is in equilibrium. So if we have a lot of GTP, it will react with ADP to give us ATP, which is why I said that consuming GTP is energetically equivalent to consuming ATP. ATP is the only phosphate source, right? The only triphosphate source in our cells is ATP. The other nucleotide triphosphates are all made from ATP. Okay, so take a few minutes here and work through the last question on your activity, which hopefully should be fairly straightforward based on the things we talked about. And then we're going to finish up today by talking about how the regulation of glycolysis and gluconeogenesis are coordinated. And y'all are going to hate it.